Topic 1, Atoms in the Periodic Table, Lesson 1, Atomic Theory, pages 4 through 13 in your textbook. Development of atomic theory. What's more than 16,000 times thinner than a human hair and can be used in fabrics to repel stains and odors? It's a nanowhisker. Nanowhiskers are tiny threads that measure about 10 nanometers. Reminder that 1 nanometer equals 0.00000001 meter in length and 1.5 nanometers in diameter. As small as a nanowhisker is, its diameter is still about 10 times wider than the diameter of an atom. And what is smaller than an atom? That's our subatomic particles, which are the nucleus, proton, neutron, and electron. So in today's lesson, we're going to learn how we discovered all of this stuff and some of the history about it. So first, we're going to do a reading check. So which two elements are nanowhiskers usually made of? And the answer to that is carbon and silver. All right, so now we're going to do the connect it. So circle one of the sea squirts on the image and read the photo's caption. So our circle should be here or any of the other sea squirts. So sea squirts and nanowhiskers, figure 1. The structure of a sea squirt is made up of nanowhiskers, or tiny threads that are not much wider than atoms. So what gives a sea squirt its unique structure and shape? And that's nanowhiskers. How might nanowhiskers be used in fabrics to make them stain resistant? Nanowhiskers are small and spaced so close together that they form a barrier that prevents substances from touching the fabric. The first theory is on atoms. So what exactly is an atom? Around 430 BCE, the Greek philosopher Democritus proposed that matter was formed of small pieces that could not be cut into smaller parts. He used the word atomos, meaning uncuttable, for these smallest possible pieces. Now we consider an atom the smallest particle that still can be considered an element. The study of atoms really gained speed in the 1600s. So, because atoms are so tiny and therefore difficult to study, scientists have created models to describe them. As more evidence was collected, the theory and models were revised. John Dalton, an English chemist, conducted many experiments centered on atoms. From these experiments, he inferred that all atoms had certain characteristics. So in Dalton's atomic theory, Dalton believed that all elements consisted of atoms that cannot be divided. Also, that all atoms of the same element are exactly alike and have the same mass. Atoms of different elements are different and have different masses. An atom of one element cannot be changed into an atom of a different element by a chemical reaction, and compounds are formed when atoms of more than one element combine in a specific ratio. Thomson's model. So J.J. Thomson discovered that atoms contain negatively charged particles. Each of these particles is called an electron. Scientists knew that atoms themselves can have no electrical charge. Thomson reasoned that atoms must contain some sort of positive charge as well. So basically, because he found the negative charge and he knows that atoms have no charge, there has to be a positive charge to balance it out. He described an atom that had electrons scattered throughout a ball of positive charge. So basically, his model looks similar to a scoop of chocolate chip ice cream. So you have your positive amount or your positive section. So if we have the scoop, the ball of ice cream that is the actual ice cream is our positive charged section. And then the chocolate chips would be our electrons that provide the negative charge. So figure 2, Thomson suggested that atoms have negatively charged electrons set in a positive sphere. Each electron is represented above by the symbol E-. What indicates that an atom has no overall charge? And the answer is that the number of positive charges equals the number of negative charges. All right, so next on scene comes Ernest Rutherford. And Ernest Rutherford found evidence that challenged Thomson's model. So Rutherford decided to do this experiment, which is known as the gold foil experiment. So figure 3, we have this set up. It's an example of the gold foil experiment and what happened. And it says that the results of Rutherford's experiment surprised many scientists. In the image of the gold foil experiment, circle the rays that you think scientists were puzzled by. And we're going to do that in just a moment, but first I want to get to some things that Rutherford and his team predicted. So Rutherford and his team predicted that if Thomson's model were correct, the charged particles would pass straight through the foil. They also predicted that the paths of some particles would bend or deflect slightly because of the positive charge that was spread out in the gold atoms. Now, if we look at the experiment, we can see that most of the particles passed right through, but a few particles were deflected at sharp angles by the gold foil. So those would be the ones that scientists were puzzled by, which would be these two here. So the ones that didn't pass through the gold foil at all, that surprised the scientist. So to go into more detail about Rutherford's theory, this is kind of an image of what is happening and how they're deflecting, and seeing more on a atomic level what's happening. So here we can see our particles. At the start of each arrow is where the particle, where it goes through, it's going through the gold atom. And then some of them are passing through just fine, some of them are deflecting, and some of them are not. So here's what figure 4 wants us to do. We need to write A, B, or C by each arrow to indicate how it supports Rutherford's model of an atom that is mostly empty space with a dense, positively charged nucleus in the center. And of course, that was what he discovered after doing this experiment. So for A, those will be like charges repel each other, and any positive particle that passes near the nucleus of an atom is deflected from its path. B, most of an atom is empty space, so most positive particles pass straight through the foil. And C, the nucleus is small but dense. Any particle that actually hits the nucleus bounces back in about the same direction it came from. So we're going to start at the beginning and work our way down. So that first one passes straight through, it's B. The next one is C because it hits that nucleus in the center and bounces back. Next, we have another B because it passes straight through. Then we finally have an A, and we can see what it means. It hits that positive and bounces off. If you have ever put magnets, so we know that when two magnets come together, one side is positive, one side is negative. If we push two positive sides together, they repel each other. They don't want to connect, they want to separate. And that's what's happening with our atoms. It's a similar concept, the same concept really. So it goes through, pushes it away. So that's how we know that's A. And the next one is also A. Then we have 3 more B's. So we can see clearly that with our B's, it's going straight through. It's not hitting anything. It's not close enough to the nucleus to affect anything. When we do hit the nucleus, it does go right back the way it came. And then if it comes close to, but not hitting the nucleus, it's just diverted in its path a little bit. So Rutherford's model itself. Rutherford concluded that the atom is mostly empty space, but has a dense positive charge at its center. This dense center is called the nucleus. Rutherford called a positively charged particle in an atom's nucleus a proton. All right, so after Rutherford, we have Niels Bohr, who is a Danish scientist and who is actually one of Rutherford's students. So in 1913, Bohr revised the atomic model again. He suggested that the electrons move only in specific orbits around an atom's nucleus. And the orbits in Bohr's model look like moons orbiting a planet. Each possible electron orbit in Bohr's model has a fixed energy. So, figure 5 here, Niels Bohr suggested that electrons move in specific orbits around the nucleus of an atom, just as the moons of the planet Mars move in orbit around it. So there we have a picture of Mars with the moons Phobos and Deimos. And you can see the parallels there. And then we have the cloud model. So figure 6, in the cloud model of an atom, electrons move rapidly in all directions around the atom's nucleus. So the atomic model changed again in the 1920s. Around that time, scientists determined that electrons do not move in specific orbits like planets do, as Bohr suggested, but instead electrons move rapidly within a cloud-like region around the nucleus. The orange cloud is a visual model. It represents where electrons are likely to be found. A reading check. So how do later atomic theories differ from Dalton's atomic theory? And the main difference is that Dalton said atoms were the smallest known particles and could not be divided. Later theories stated that atoms are made of even smaller parts, those smaller parts being the proton, electron. So now we're going to do this model it. So the historic models of the atom can be compared to real-life objects. For example, Thomson's model was compared to chocolate chip ice cream, and Bohr's model was compared to the orbit of the moons of Mars around the planet. So we need to develop models. In each box below, draw a real-life example of something that can be used to represent the model of the atom. Do not use the example used in this text. So, for Dalton's model, we could use a bowling ball. For Thomson's model, we could use a chocolate chip cookie. For Bohr's model, a wood cookie, which is what you call a slice of wood, or anything that really has rings to it. And then for the cloud model, we can just use a cloud because that's what it's showing us, that the electrons are in clouds and not in rings or circles. All right, now a modern model of the atom. English scientist James Chadwick showed that another particle exists in the nucleus of atoms. This particle is called a neutron. It took scientists a long time to find this particle because it has no electric charge. Neutrons, protons, and electrons are known as subatomic particles. A subatomic particle is any particle smaller than an atom. Figure 7 here, we have an oxygen atom, has a nucleus made up of positively charged protons and neutral neutrons. The nucleus is surrounded by a cloud of negatively charged electrons. In the figure, label the protons with a plus sign. So here, every green is a proton, and every one should have a plus sign on it. All right, so we know that most of an atom is made up of the space in which the electrons move. And this space is huge compared to the space taken up by the nucleus. So I want you guys to imagine holding a pencil while standing in the middle of a football stadium. If the pencil's eraser were the nucleus of an atom, its electrons would reach as far away as the top row of seats. That's pretty far and pretty small. So particle charges. In most models of atoms, protons are shown by a plus sign. The symbol for a proton is P+. Electrons are shown by the symbol E-, and neutrons are represented by an N. Electrons can also be shown as a negative sign in this helium atom. So you can either use the E-, the P+, or a plus sign, or a minus sign. So according to the scale used for measuring charge in atoms, protons have a charge of +1 and electrons have a charge of -1. Because these amounts are even, the charges balance, making the atom neutral. The number of neutrons present does not affect the charge of an atom because neutrons have a charge of 0. Comparing particle masses. So when it comes to the masses of particles, protons and neutrons are about equal. Electrons, however, are much, much smaller. It takes almost 1,840 electrons to equal the mass of one proton or neutron. Atoms are much too small to be described by standard units of mass, such as grams. So scientists usually measure atoms using atomic mass units, or AMUs. A proton or a neutron has a mass equal to about 1 AMU. All right, so masses of atomic particles. An adult rhino can have a mass of 1,400 kilograms. The mass of a small egret, which is a bird, is about 0.76 kilograms. What is the ratio of these two masses, and how does this ratio compare to the ratio of the mass of a proton to the mass of an electron? So, if we take 1,400, multiply that by 0.76, it is equal to 1,842.1, which is about the same as the proton to electron mass ratio. All right, so the next thing we need to do is complete this table. So, we know that we have a proton as a particle, a neutron, and an electron. Our symbols for each thing, our symbol for a proton is P+, the neutron is N, and an electron is E-. Our mass, or AMU, in AMUs, for a proton and a neutron are both equal to 1. Atomic number. What can atoms tell us about elements? The number of protons in the nucleus of an atom is the atomic number of the atom's element. The definition of an atom is based on its atomic number. For example, every oxygen atom has 8 protons, so the atomic number of oxygen is 8. Over here, we can see how an element is set up on the periodic table. So we have our atomic number at top, then we have the chemical symbol, and then we have the element name, and at the bottom we have the atomic mass. Next, we're going to get into isotopes. So all atoms of an element have the same number of protons, always. That never changes. The number of neutrons, though, can vary. Atoms with the same number of protons and different numbers of neutrons are called isotopes. An isotope is identified by its mass number, which is the sum of the protons and the neutrons in the atom. The most common isotope of oxygen has a mass number of 16, which means that there are 8 protons and 8 neutrons. And it may be written as oxygen 16. Most naturally occurring oxygen is oxygen 16. The two other stable isotopes are oxygen 17 and oxygen 18. All 3 oxygen isotopes react the same way chemically. The number of electrons affects chemical reactivity, and neutrons generally do not affect chemical reactions very much. So all isotopes of oxygen have the same number of electrons. So our reading check. Why do you think the mass number includes only the number of protons and neutrons? And our answer is that the mass of the electrons is too small to affect the overall mass. All right, so now for the math toolbox. We're going to take the information that we've learned about isotopes and put it to use. So most elements have several different isotopes, and they usually differ in abundance. For example, oxygen 16 makes up more than 99% of all oxygen atoms. We need to use the information that we know about isotopes to complete the table with information about oxygen isotopes. So, we know that every oxygen atom has the same number of protons. So, oxygen 16 has 8, which means oxygen 17 is going to have 8, and oxygen 18 is going to have 8. Also, we know that when we add the neutrons and protons together, we get the isotope number. So, oxygen 17, we got 17 because 8 and 9 is 17. So 8 plus 9 equals 17. Oxygen 18, 8 plus 10 equals 18. So for oxygen 16, 8 plus 8 equals 16. All right, so for the second part, we need to complete the table with the mass number, number of protons, number of neutrons, and number of electrons for the elements shown. So we have fluorine, and we know the mass number for fluorine is going to be 19. The reason that we come up with this is because there are 9 electrons. If there are 9 electrons, we know there are 9 protons. And 9 plus 10 equals 19. Argon is 40. There are 22 neutrons. So if we take 40 minus 22, we are left with 18. 18 plus 22 equals 40. There are 18 protons, so we know there are 18 electrons. With calcium, we know there are 20 electrons, so there's also going to be 20 protons. The mass number is 41, so then we can determine that 20 plus 21 equals 41. As we said before, the electron number for argon is going to be 18 because they're always the same. Well, when we have a regular element, we are going to always assume that the proton number is equal to the electron number. All right, and that brings us to our lesson check. So, number 1, how did the discovery of isotopes disprove one part of Dalton's atomic theory? So, Dalton's theory stated that all atoms of an element were identical. Isotopes are atoms of the same element that differ in numbers of neutrons. All right, so in Rutherford's experiment, why were some particles deflected a small amount? And those were the particles that passed near a nucleus. So they were positively charged and they passed near a nucleus that was also positively charged. And so then the like charges repelled each other. 3. This diagram shows a hydrogen atom. Explain why it looks like it does. So the green area represents the 1 proton. There's only 1 proton in the nucleus of hydrogen. The orange area shows an electron cloud around the nucleus, where the electron is likely to be. 4. An atom of chlorine has an atomic number of 17 and a mass number of 37. How many protons, neutrons, and electrons are in the atom? So we know that there are 17 protons because that's the atomic number, and there are 17 electrons. We also know that there are going to be 20 neutrons because 37 minus 17 equals 20. 5. An atom of carbon has 6 protons. In the space below, use the knowledge you gained in this lesson to draw a model of a carbon atom. Be sure to label the protons, neutrons, and electrons in your model, along with areas of positive and negative charge. So your model should look something like this. We want to make sure in ours that we can see the 6 protons and the 6 electrons and the 6 neutrons. So we want to make sure that we can see all of that in our model. And that finishes lesson 1.